a 0 or 1, it's now giving it a label that is the number of the object to which it belongs, right? So if there is just one object, everything will be a 0 or a 1 in the 1, right? But if there are two objects, there'll be 0s, 1s, and 2s, all right? By the way, one of the things that we're not going to talk about is when we talk about a pixel being connected to another pixel, there's what's known as 4-way connected and 8-way connected. 4-way means that you're connected to north, south, east, and west. Did I get those right? Well, it depends upon which way you're looking. 8-way connected says I'm connected to north, south, east, west, and I'm connected to northeast, northwest, southeast, southwest. All right. For what I'm going to show you here, we're going to assume a 4-way connected. The algorithm is pretty much the same if it's 8-way. There are a variety of connected component methods. The one that most people use is referred to as row by row. And it's sort of classic algorithm and simple to go through. And there are some efficient speed-ups that were used so you could run it quickly in industrial systems. But these days, running your connected components is rarely the thing that's taking your time because the machines have gotten much faster, and the algorithm itself is pretty straightforward row by row. So let's start with a picture that looks like this, okay? So we've got 1s and 0s. And if you look carefully, you'll see there's really only one object here. Okay? Those are all the 1s. And what we want to do is we want to eventually determine that all of them should be labeled as a 1. Okay? But the system doesn't know this yet. All it knows is that there are 0s and 1s in the pixels. All right? So here's the algorithm. We start with a variable at 0. And what happens is we go across, okay? And when we find a new pixel, if it's not connected to anything before it or above it, and of course there's no above and there's no before, we'll increment our counter, all right? So we start labeling this one as a 1, and then we go forward, and then we're not connected, and then we would get to here, and so what would that be labeled? What comes after 1? 2, okay? So we label that as a 2, so this is going to become a 2, right? And then goes over here, and then what are we going to get to when we get to the next one? What are we going to label that? 3, okay? So that works fine. The reason that this one is listed as a 1, even though you've scanned it, is it's connected to the one above it. You say, oh, I'm connected, so I'm a 1. Likewise, when I get over here, it's connected to the one above it. So these are all labeled as 1, 2s, and 3s. But you see where it says here, remember conflicts? All right? As I'm going through, when I'm labeling this pixel, okay, I now have a conflict. Because when I look behind me, it says that I'm a 1. And when I look above me, it says I'm connected to a 2. So what I do is I pick one of those, maybe the 1, but I remember that I've got a conflict there. Likewise, I have a conflict here. And what I learn is that 1 is the same as 2 because it's connected there, and 1 is the same as 3, so it's connected there. So after I'm done labeling all of these, and I've got 1s, 2s, and 3s, I relabel everything as a 1. Because all the 2s get relabeled as 1, all the 3s get relabeled as 1, and that way the system knows that there's exactly one object, and all the pixels with the 1s are the pixels from that object. And it works just like that, and it works great. Here's an example from that CT cross-section I was showing you before, and you can see that after some various other operations that we'll talk about in a minute, it's able to label these different elements, okay? And what's nice is those elements have semantic meaning to the radiologist who's looking at these things. You know, it's also useful for if you have some clustering algorithm. So here you are seeing just them clustering pixels in a beach. Well, it's not much of a beach, is it? No. Ugh. Okay, it must be the Northwest. No sand, just muck. Sorry, Seattle. And you can see they're labeling these different things using connected components. I mentioned the idea of doing mathematical morphology. That is, fixing up your picture. Okay, and fundamentally, there are two basic operations, and they're referred to as dilation and erosion. We're going to go through both of those in detail. Once you have those two basic operations, you can combine those to make more operations. There are a whole bunch of them, and this used to be a whole industry doing mathematical morphology. The ones that we use most to date, or I should say the ones that we use most currently, are various forms of closing and opening, and we're going to talk about those. Then there's thinning and thickening and a few other things, but they all stem from these two basic operations of dilation and erosion. So let's go through those. So dilation is exactly what it sounds like, right? When you dilate something, it expands. And so dilation expands the connected set of ones in the binary image. So here you see this thing expand as you get bigger and really, just grew out. And we're going to talk about the mechanisms by which you do dilation and something called the structuring elements which control the shape. This one is an interesting one, right? Everything expanded and has two effects. First of all, things got a little straighter, but also notice that these little cutouts went away. Likewise, when this thing got bigger, okay, the holes went away. Dilation in general can be used for, like it says, filling holes and gaps. The inverse, converse, reverse, the other of dilation is called erosion, okay? Erosion, just like when beaches and other things erode, is you're essentially shrinking the shape, right? So this big bar becomes a narrower bar, this big circle becomes a smaller circle. Here's where you start to see its power, right? These two connected sort of elliptical things become, well, here in this case, it's these two circular things. You could actually do it, go from those ellipses to circles. Important thing is that that middle part went away. And here you see that these little protuberances went away when the entire thing shrank. And that's referred to as erosion, okay? To go over the mathematics of both dilation and erosion, we have to talk about something called the structuring element, okay? The structuring element is a mask, okay? It's a shape that you're going to use to do these operations. And it can be any shape. For today, the shapes are going to be just ones and zeros. They can also be ones, zeros, and x's, and the x's are don't cares. But nothing we're going to talk about today will involve don't cares, so I'm not going to talk about it. What's important about the shape is that they all are defined with respect to sometimes called an anchor or a reference point or an origin, right? And usually, not always, usually that origin is in the middle of whatever shape you're making use of, okay? So given a structuring element, we can define both dilation and erosion. So dilation is as follows. Basically, I've got some binary image, B, okay, and that's here. I've got a structuring element, S, and the structuring element has to have an origin. Basically, what you do is you're going to take this dilation structuring element and you're going to run it around here, placing the origin at different places. And wherever you place it, you're going to take the OR of all of the ones in the structuring element with the ones underneath it. And so what that means is if any of the ones of the structuring element land on a 1 in the binary image, the OR of all that will be 1. So Arpin did this, and he's very proud. So there's my structuring element, and there he goes. Very good, cool. All right, so you basically run it all over, and what the result of this, okay, is this thing here. And let's just take a look at that, right? These are our two original ones, okay? So when I put this structuring element down here, like that, nothing was a 1. In fact, as I slide it all along, nothing is a 1, so those are all zeros, right? But when I put my structuring element here, notice it overlaps there. Okay, so this value, which is the origin for that first position, that gets a 1. And as I slide it along, that's how I get the rest of these. So that's dilation by a particular shape. Now, I will tell you, sometimes you'll dilate by sort of a funny shape like that. Usually your shape will be symmetric. Sometimes it'll be taller than it is wide because you're trying to extend things in one direction as opposed to another. But this cutout kind of thing would be a little bit unusual. In fact, here's a nice example. So here's a binary text, and you can see that there's white pixels, but they've got lots of, if you take a look at that M, you can see there's kind of a bunch of little spots in there that seem to have some holes in it. So if I use a structuring element that looks like this, that essentially says if I touch anybody to my right, left, up, or below, I want to turn on the pixel. And when I do that, you get the really much better result, right? I mean, it's much easier to read the one on the left than the one on the right. The one on the right might be uglier, okay, because it doesn't look so crisp, but there's no question about reading it. So here's the quiz, all right? So what's the result of this dilation? Basically, remember, what you're going to do is you're going to say, here's our origin. Where, when I put this structuring element down, will its ones touch the ones in this picture, right? Well, the answer is here, and you realize, actually, almost everywhere. In fact, the only places you can put this structuring element down and not touch a 1 is over here, right? Because this is a 0, and this is a 0, and there's nothing over here, right? And I can put it over here, because this is a 0 and this is a 0. Everywhere else, so for example, if I put that structuring element here, I touch that. If I put structuring element here, I touch that. Likewise, everywhere else in the picture, I touch a 1, and that's why it looks like that. Erosion, in fact, in some sense, is easier to even think about. Again, I have a binary image B, and I've got a structuring element, okay? And now my structuring element is this little tall column here of just 1s, and its origin is in the middle. And the way erosion works is I take my structuring element and I run it over picture. And what I'm going to do is I'm going to take the and of the 1s in my structuring element with the pixels below it in the image. And I take the and, well, that means that all of them have to be a 1 for it to be a 1. So another way of saying this is when I put my structuring element down, all of its 1s better touch 1s in the underlying image, or I'm going to set the value to a 0. So before we take a look at what the result is, let's think about where can you put this thing down in this picture such that it touches only 1s. And you realize, well, I could put it here with my origin there, right? I could put it here with my origin there, and the same thing over this column, and that's the only place. And that's why the result of this is this right there. And by the way, I guess I didn't mention the other one. This circle with this minus on it, that's referred to as erosion, and the circle with a plus, that's the dilation nomenclature, okay? Show you an example of erosion, and here we're eroding with a disk, a circular disk with the origin in the middle, okay? So this is the original image. We saw this one before. And if we erode with a disk of radius 5, you can see that what's going to happen is, first of all of these lines that are thin, they all go away. Why do they go away? They're thinner, obviously, than the size 5, or actually it's radius 5, so they're thinner than size 10, all right? And so there's no place you can put that disk down and have the pixel survive. Obviously, there's one stretch here that's thick enough, and so that lead survives. So if I make the radius bigger, this thing, they all go away. And if I made the radius even bigger yet, what happens is all these leads go away, and also you notice this square is shrinking by that amount, because the only place that you can fit that inside there is at this level, and so it's going to pull away from the edges. So that's erosion. Now, as you saw, dilation fills holes and stuff, but it grows your picture. Erosion removes little things you might not want there, but it shrinks your picture. I don't really want to grow or shrink my cells. I just want to disconnect them. Not my cells, the cells in the picture. So I don't really want the things to get bigger or smaller. I just want to clean them up. Well, so that should make you think, probably I could do some eroding followed by some dilating, or some dilating followed by some eroding, and you'd be exactly right. And those two operations are referred to as opening and closing. And I say here the two most useful binary morphology operations. That is just one man's opinion, my not so humble opinion, that's probably the most important thing. And the only reason I say it's most important is in many systems that I've worked on, down in the guts, somewhere we're doing some opening and closing just to clean up our binary images a little bit. So opening is a compound operation. So erosion, dilation are primitives. And it's a erosion followed by a dilation. Okay? So that's what a opening is. And it says here you can show that an opening of something of A by B is the union of all the translations that fit entirely within A. That's kind of complicated and wordy. It's much easier to see in a picture. So here's our binary thing A, and this is our structuring element B. And the opening is all the places, all the translations within A that you can fit B. And when you do that, you would get out this thing here. And you'll notice that it has broken the connection between those two triangles, and it's also rounded the edges. So it's not surprising that it's broken them, because it's too small and the whole thing doesn't fit there. And the rounding is because of the shape with B. It says here, and Jonas' slide. The opening is the area that we can paint when the brush has a footprint of B, and we're not allowed to let the brush get outside of the original image A. One of the other cool things is if you take a look at this, if I now have this shape, I were to open with B again, well, it fits everywhere inside of there, so